So, well, it's great to be here and seeing a lot of people I haven't seen in a while. Okay, so this is going to be, yeah, I'd say the renormalization part is going to be next time and the time after more. So I wanted to, so I think I'm giving 3 talks. I wanted, first of all, just to kind of outline, or say what I was going to do in each of these talks, kind of briefly, and then get to what I'm going to do in this talk. Can you guys in the back see this okay? Okay, great. So today, I'm just going to talk about, well, so just I'm going to talk about maybe inner polygonal. So, and then I was just going to start with kind of some basic things, billiards in the square, and just a tiny bit about rational billiards, maybe just enough to sort of give you a sense of why rational billiards is such a deep and massive subject. And then I was going to veer off and talk a lot about irrational billiards, and in particular about triangular billiards, and I was going to show off this program that Pat Hooper and I wrote years ago called McBilliards. I was going to explain how it works and what it does, and with a view towards, there's kind of various kinds of billiards. I was just in Heidelberg, and somehow people were really impressing upon me that there's really 4 kinds, and inner billiards is one of them. The other kind I'm going to talk about is outer. So outer polygonal billiards is a game that you play on the outside of a table. One way, somehow inner billiards is a game you play on the inside when you care about length, and outer billiards is a game you play on the outside when you care about area. So once you've heard that, you might guess that there's 2 other things you could do. You could play on the inside and care about area, and play on the outside and care about length. And one of these things is called simplectic billiards, and then the other one I think just doesn't have a name yet. But anyway, so I may at some point talk about these kind of 4 kinds. But really, I'm going to talk about these 2. They live in a little checkerboard pattern or something. There's kind of two really classical results about this. One is that if you have a polygon when all the vertices are rational, then every orbit is periodic. So that I'm going to explain something about that. This result seems so foundational that 3 teams of authors prove this in succession. And then another basic result is about what happens like on the regular pentagon. And Sergei Tabachnikov probably was the first person who analyzed this. And somehow this is where you see like a renormalization in the system. So I was going to explain somehow the rational case, and also what happens for pentagon. It's sort of interesting that somehow, like sometimes, like the problems that are hard here are easy here, and vice versa. So I'll try to explain that. And then the third thing, maybe I'll talk more specifically, more. And in particular, so I did a lot of work about outer billiards on kites. This turns out to be a very fruitful thing to do. So I was going to talk about that. And by talk, I mean kind of showing off the program. So after some time, I wanted to start using these programs and showing you guys what they do and how they work. So that's the plan for the 3 lectures. And then maybe just to say more about the first one, for today, I'm just going to talk about, I'll talk about the square, and then the rational case, and then triangles. Okay, so that's the plan. And again, mostly I want to show this program with billiards. Okay. Any questions so far? I guess I haven't really done anything. And I'm really it's going to be really, especially in the beginning, just very kind of elementary and just giving basic definitions and things like that. So that's the plan for the mini course. And then there's a problem session, and in the problem session, I hope to, well, firstly, I'll explain some unsolved problems, and even more that I don't say here, but I hope to maybe share some of the software if some of you are interested in doing experimentation. If you want to program in Java, this is great, because I've got all this Java code laying around. I mean, Java has some nice features. The bad features, it gets a little bit worse every year, but otherwise it's really good. Okay, so billiards. Okay, so firstly, what in general, what is billiards? I mean, in billiards, I mean, you have some kind of shape, and then you have a point that's moving, and then it hits the boundary of the shape, and if the shape is smooth, then one way to say it is it makes a perfect K. The angle here is the same as the angle here. And if it's a smooth shape, you would use the tangent line to say what you mean by the angle. If it's a polygonal case, then it's even more obvious what it means. So basically, when you play billiards, you just start with a point, and then you bounce around, and you just keep going. If you might hit a corner, in which case the traditional thing is just to stop, say it's done, or for example, you might come back and retrace the same path again, and then it would be a periodic billiard path. So one of the, just broadly speaking, I mean, two kinds of basic questions are like, if you have a table, a shape like this, and you play billiards, are there any periodic billiard paths? And if the thing is, say, smooth and convex, the answer is yes. But it's unknown for polygons in general. If you have a polygon, is there a periodic billiard path? It's not even known if every triangle has a periodic billiard path. And as far as I know, it's not known if there's any polygon with no periodic billiard paths. So this is a kind of central question. Or even more generally, you could play the same game in higher dimensions, say where you're bouncing off the walls, and you use the same condition about the angles. And it's unknown if there's any polyhedron with no periodic billiard paths, or any 100-dimensional polytope. I mean, you suspect the answer is probably no, because I mean, why is the thing going to come back in high dimensions or something? But anyway, that's not known. I might talk a little bit towards the end about some experiments I did with some tetrahedra. But anyway, that's a basic question. And then another kind of basic question is somehow like the sort of, you might call like either what people call mixing or ergodicity properties of the, well, without saying those kinds of words, you could just ask, like, if you start in a path, is it true that it becomes dense? In other words, if you just let it run forever, it becomes within any epsilon of any point. So there's just a question about kind of the density of periodic billiard paths. And then you can ask kind of finer questions, like if you pick two regions of the same area, does the billiard path spend in the limit sort of the same amount of time in each of those regions? So there's finer questions like that involving measure theory. And for rational billiards, in the case when all the angles are rational multiples of pi, firstly, there are always periodic billiard paths. I think I'll walk you through a proof of that. In fact, there's kind of lots and lots and lots and lots and lots of theorems about this. And then also, likewise, questions about, does the path go everywhere? In certain cases, there's all kinds of results. But let's just say, so I would say somehow the square is maybe it's sort of like, this is something like the Garden of Eden. It's like, you know, everything is, you know, known and perfect and beautiful, and then the rest of billiards is sort of designed to kind of recapture some of this perfection. And so what happens in the square? Well, I mean, the first thing to think about with the square, let's see, I guess this. Okay, all right. It might be good to draw the square half the size, and here it's when you do billiards in the square, it's sometimes simpler just to think about what's happening in the torus. So there's a 4-to-1 map from the torus. So this quarter of the torus maps in like this, and this one maps in to reverse the R, and so on for the other pieces. And if you watch this go over, like if you have a straight line here and it goes over here, this has the effect of actually creating a billiard path for you. So this operation maps things which are straight lines or locally straight lines in the torus to billiard paths. And conversely, if you have a billiard path in the square, you can just, so to speak, lift it to the square. You sort of start in the same place, and then rather than bouncing off, you just go straight. So you can think of the square torus as being a kind of, people call this something like an unfolding of the square. And so rather than think about, you know, one thing that's a little bit annoying about the square, or any billiards for that matter, is that somehow the path is going in different directions at different times. And if you say, well, rather than study billiards here, I'm just going to study what's called the straight line flow. I'm just going to start at a point and move in a straight line. Maybe I'll give some of you a break and I'll write on the other side. Is this big enough for you guys to see? So here are some things you can see right away. Like, suppose you start and you go at a slope which is, say this whole height is 1, and you go at a slope which is an irrational slope. Then, you know, what happens? I mean, you go straight, and then when you come back, you've gone up. If S is the slope, then you start at some point, and then you rise up S when you come back to this wall, and then when you repeat, you come back to S, and you'll never get the same value because S is an irrational number. 2S will never. You're computing 2S mod 1, and you know you're computing k when you come back k times. You're computing ks mod 1, which means you just subtract off integer parts and see what you get. And if this ever was equal to what you started with, then S would be a rational number. So somehow these are not periodic, and dynamically speaking, you would call this the first return map to this. It's really a circle. This first return map, it's the circle you could identify with R mod Z, and then this is just the map X goes to X plus S mod 1 or mod Z. And this is question?
What do you do if your billiard ball runs into the corner?
Okay, well, like I said before, I mean, you kind of stop the game. I mean, that's a good point. There's a slight, maybe an advantage to playing on the torus, because on the torus, if you go into the corner, and the torus doesn't know it's a corner. So you can do one of two things. You could say, well, I'm just going to forget about, you know, I could say, well, it's not quite a kind of a total bijection between the straight line flows and the periodic I mean, in the billiard paths, somehow it is for the ones that avoid the corner. So you can take your pick as to what you want to do. One thing you could do is, on the torus, you have translation, and so you could translate a little bit down, and then it would miss the corner. But it's a good point. I mean, on the torus, it doesn't even notice that it has corners. So I say you could do it. I mean, you can decide what you want to do. I would prefer not to worry about the corners and just go. But anyway, this kind of map, if you think about it, I'm not going to prove this, but if you take a circle and you rotate it by an irrational amount, then every orbit becomes dense. And maybe the intuitive idea is you start rotating around, you produce like these points which are like a polygon, and then the next time it goes in between where it was before, and it just keeps kind of filling it in. And if it really left a gap, you could move that gap around, and somehow you wouldn't be able to find any orbits at all. Maybe that's a kind of a quick sketch of a proof. But anyway, for things like this, the orbits are dense. And so if you take a square and you take an irrational direction and you bounce things around, then you get a dense orbit. So somehow from this picture, it's a kind of a neat little theorem that if you pick an irrational slope, then this thing fills up the entire square, so to speak. And you can see it by you kind of lift to the torus, you do the straight line flow, you intersect with the side wall, and now you have a one-dimensional rotation of the circle. And this is a kind of a template for a lot of arguments in rational billiards, which I'll explain a little bit. Again, this is kind of Garden of Eden case. What about rational slope? Well, now I'm really going to focus on the corner. So let's see. So I mean, since the torus is completely, translation, it has this translation symmetry. Let's just. Okay, I got to draw sort of a smallish torus, and maybe my slope is 3/2. Well, I didn't quite get this right, but if it's 3/2, the thing's going to go and it's going to hit this point here, because it goes over 2 squares and up 3. I'm thinking of just taking the torus and then just sort of unwrapping it in the plane. If you like, I'm taking the universal cover of the torus. But anyway, for any rational slope, you eventually hit another corner, and then on the torus, you're just closing back up. So, and in the torus, this thing, well, okay, I won't embarrass myself by drawing it in the torus, and this isn't a very accurate picture, but you'll get something here which closes up. So each rational slope will give you a periodic billiard path, and then also it's just convenient. I mean, if you wrote down 6/4, you would get kind of a longer periodic billiard path that just went around twice, and so on like that. And conversely, so this gives you a nice way to count. Say you want to know how many periodic billiard paths are there of length less or equal to n. Well, you might as well just translate them all down so that they start at the origin, and then you're reaching some other integer point in the plane, and conversely. So and what is the length? It's just the distance of the point you hit to the origin. So how many are there? Well, essentially they're in one-to-one correspondence with the number of lattice points inside the disk of radius n, and that, as you probably know, that's like computing the area of the disk. It's asymptotic to pi n squared. So somehow you get this you get this asymptotic formula for the number of periodic billiard paths. You might only care about the ones that go once around, rather than this counts them all. If it goes 7 times around and has length less than n, it's still counted. If you just want the ones that go once around, you have to take this number and either divide or multiply by something like zeta of 2, like pi squared over 6, because there's some kind of number theoretic trick which will eliminate the ones that go more than once around. Just counts the ones where the, anyway, I won't go into that, but you can count both things, either the ones which are called primitive that only go once around, or just all of them, and you get this exact asymptotic formula. It's just, the number over n squared is equal to pi. What could possibly be nicer? But actually, it's a famous unsolved problem to guess, like, how well does this thing approximate pi? Like, if I take, just call it like, number sub n over n squared. This is, about equal to pi. But, or maybe I should write it like this. Then there's some kind of error term which grows slower than n squared, and this is one of Gauss's problems. And the answer is conjectured to be the error term is supposed to be about square root of n, like it grows faster than n to the 1/2 plus epsilon. And so anyway, the answer is conjectured to be about root n, but it's a famous unsolved question. How do you get the next term in the expansion? So anyway, so that's all I want to say about the square. You have, in the irrational directions, you can say quite a bit about what the path is doing. It's just sort of equivalent to an irrational rotation. And then in the periodic direction, you can count them in a very accurate way. You get this kind of exact asymptotic, and it's sort of as good as it gets. So now I'll move on a little bit, and I'll talk about something about the rational case. So I'll try to say as much as I can that's the same. So the first thing we did was we took billiards in a square, and then we kind of produced a surface that maps to the square and converts straight line path on the surface to billiard paths on the square. So let's go for a rational So rational means that all the angles are pi times p over q, where p and q are integers. And the square is pi times a quarter. And the first thing is, so there's this construction called the Katok-Zemelikov construction, which basically does for any rational polygon what billiards does for the square. It's going to produce a surface and a map to the original polygon, which converts the straight line motion on the surface to billiards on the square. So let me explain. I'll explain this in three ways. The first way is kind of intuitive. I mean, you have a periodic billiard path, and every time you hit a side, rather than bouncing the ball, you just continue the ball in a straight line, and you reflect the table. So you'd have approximately some table like this, and then you hit this one, and then you reflect again. And of course, this is going to make a horrible mess in the plane. But what you could do is you could sort of move these things far apart from each other. And so what you'll see is a bunch of copies of the table in various orientations. And you'll only, even if you do this forever for any billiard path, you'll only see a finite number of things in finitely many orientations. And then you just glue them back together, remembering where they came from in the billiard. So even if I just kind of snap this one off, I remember that they're actually supposed to be glued together along an edge. So what I would get is a finite number of polygons in these various orientations, and then I glue them together, and this gives me locally a surface. There's one kind of neat feature, which is that if you go what happens around a vertex, So this is kind of a little bit counterintuitive, but what happens is you get that you won't get a flat surface like the torus necessarily. You might get something which goes around some integer multiples of pi, or actually of 2 pi. So this thing, an example to keep in mind of that kind of surface is the regular octagon. You take the regular octagon and then you glue opposite sides by translations. And then if you figure out what happens around each vertex, then this thing goes around 3 times before you come back. So this is an example of a surface that's called a translation surface. It's completely flat, except in this case there's just a single cone point, which comes when you glue opposite sides. All of these 8 points get glued together. And also, moreover, there's also it's a little bit more structure, because you also sort of know what vertical is everywhere. So it's a surface that's flat everywhere, and except for these finitely many points, in this case 1, and plus there's a notion of a what's called a parallel vector field that's globally defined. So that's what a translation surface is in general. It's a surface that's locally isometric to the Euclidean plane, and it's except for a finite number of singularities, which sort of look like you're just going around some multiple of, some integer multiple of times, so they look like what's called a cone. These are called conical singularities. And then plus you have this vector field. So the vector field, when you do this construction, if you take the billiard path like this, all these things, if you start in the same direction, you're always getting kind of your vector field is just kind of defined in the pieces. And so that's where this extra piece comes from. So that's sort of maybe that's one way to describe it in a way which makes it not completely clear that it's going to work. Maybe I'll say another way to describe it. You can on the polygon, you can think about a 3-dimensional space over the polygon, which is something like you would call it the kind of unit circle bundle of the polygon. What it is a point in the unit circle bundle is a point together with a direction at that point. So at each point in the inside, there's a circle's worth of directions. And then at the boundaries, there's a half circle's worth of directions. So you have this thing. It's not quite, it's a little bit funny at the boundary. And now if you start with your polygon in some direction, this will give you a kind of a sheet inside this circle bundle. It's sort of like at each point, in the polygon, you just have the point, but in the circle bundle, you have the direction as well. And so inside this 3-dimensional space, you have a kind of copy of the polygon. And then when you hit the boundary, you identify this vector with, at the boundary, it kind of looks like a wall, and you're taking this wall and you're kind of folding it up according to the billiards rule. So you have this kind of, so then the sheet kind of goes and it hits, and then it kind of continues around and makes another sheet inside, and then it hits again, and you get these finitely many sheets inside this 3-dimensional space, and they just kind of naturally fit together to make the translation surface. So that's another way of, in brief, you kind of lift this to what's called the unit tangent bundle of the orbifold, and then you just continue where it goes. And I just wanted to say this other way just to point out that there's various ways of making this construction completely rigorous and precise. But I hope this gives an intuitive feel for what the surface is. It's just kind of, and then you have, you can do the straight line flow on the surface, and then there's a projection back to the polygon, because each of the pieces just came from the original. So again, there's this map. So why doesn't this work in the irrational case? It's because because like somehow if you start doing this process, you could get the polygon will end up in an infinite number of orientations, and you can still do it. You just will get a surface that doesn't have it's sort of an infinite surface. And some people in this room have studied this. For instance, when you do this for right triangles, it's quite a beautiful thing. So if you're interested in understanding what this construction does for things which are irrational, try it for right triangles. You get this. Yeah, question?
Wouldn't it be more natural to just abandon the Euclidean shapes and take hyperbolic shapes and then sort of make it?
That's a great, that's a really good point. You could do that. It would completely change the dynamics. Like, because the straight lines in the hyperbolic geometry would not be related so well to the straight lines in the. So the thing that's working for you here is that you have these surfaces, and then the geodesic flow or the straight line flow on the surface corresponds to the billiards in the polygon. It's an interesting thing. Like, here's an interesting thing. This regular octagon. One of the other really beautiful things about the regular octagon is if you make it a hyperbolic octagon with just the right angles and you glue it together, you get a hyperbolic surface of genus 2, and that thing's great. But then, the geodesic flow on that thing is not related to billiards in the Euclidean octagon. It would be related to kind of hyperbolic billiards in the hyperbolic octagon. So you would just, if you change the geometry of the surface, you're now studying a different kind of billiards. And it's a really, but it's neat. Like, somehow, maybe this is a kind of a very modern point of view that, like, somehow, like, these kinds of things, when you could do this for like a regular 10-gon or 12-gon, or you could have one general construction for these things, which is easy if you want to build them, these translation surfaces. Well, you could start with a rational polygon and then do this construction. But another thing is you can take a finite number of polygons and just arrange that each edge on one of the polygons has a partner edge somewhere else that's parallel and the same length, and then just glue the partners together, and this will automatically build you one of these things. So these, and somehow you could also like make them hyperbolic. So somehow there's like sort of a kind of, these surfaces kind of wear two geometries. One of them is this kind of translation surface geometry, and the other one is hyperbolic geometry. And it's sort of, you start playing with this and they seem suspiciously similar. Like, I could take this octagon and I could sort of lengthen the top and bottom side and then glue it back together. And then this would give me another different translation surface. And I can also change the hyperbolic geometry. And then it turns out that somehow the dimensions of the spaces of these things is the same. And they're very closely related. You can somehow get from one to the other if you're willing to swallow sort of fancier kinds of mathematics. Like a translation surface is something like a hyperbolic surface equipped with a quadratic differential. And then when you integrate the quadratic differential, it gives you coordinate charts into the plane, which impart the other structure. So somehow anyway, that's a great, okay, that question could go on forever, but that's part of why it's so deep. There's a kind of connection between these translation surfaces and hyperbolic geometry. Yeah, question?
The translation surface that we get for a billiard with a closed trajectory, it also has boundary, isn't it?
The surface, it doesn't have boundary because from this reflection process, every time you go through thing, you're gonna produce a partner polygon which has a parallel edge, and you're gonna just glue them together. So there's no, that's the amazing thing. There's no boundary on these things. Yeah, it's just like on the torus. When you take the square and you start reflecting it, you.
Can you elaborate? Like, I start from one copy of this polygon.
Yes.
I cross an edge. Okay, I produce a second copy. I glue by that edge. What happens with other edges?
It's better to say it like this. You look at all all your angles are going to be something like pi over k pi over n for fixed n and various k. So you just take all possible orientations rotating by k pi over n. You put them disjointly in the plane, And then you remember how they glue together. Like in each edge of one, there's going to be, if you hit it with a billiards path, you're going to go to another one. And so every one of these polygons has a partner edge that's the same length and parallel, and you glue it together. Yeah, that's amazing. There are no edges to this thing. All there are these conical singularities. So I want to say one more thing, and I'm finally going to, this is the problem with rational billiards. It goes on forever. Yeah. You just, it's the same thing. It corresponds, so you hit a corner and you stop. Sometimes some cone points will be something like in the torus, they were sort of invisible because you went exactly once around. Yeah. But maybe you go more than once around. And so if you go once around, you could choose to ignore it or choose to notice it. And if you go more than once around, you're kind of stuck. Like you hit it and then you stop. The billiard paths which go from one cone point to another are often called saddle connections. And some people in the room, yeah. Anyway, there's some experts here. And you also sometimes you'll count periodic billiard paths, and sometimes you'll count saddle connections, and it's almost the same thing. Because if you have a periodic billiard path, you can kind of slide it along until it sort of hits a corner.
So for now, we can just understand that we're just like removing measure.
Yeah. In fact, you're just removing a finite number of points. That's right. Sure. Okay. So maybe I'll stop there because I want to say something about irrational billiards. But then people study. Okay. Anyway. There's more to that. But again, there are people in this room who are vastly more qualified to say more. I want to talk about the irrational case. So again, maybe it's unknown that if every triangle has a periodic billiard path. So maybe I'll show this program that Pat and I wrote. Can you guys? Can you guys see that? So there's a big window on the top with a black screen, and that's when I'm moving a cursor around in that window, and then what you're seeing here is a triangle, and you're also seeing a periodic billiard path in the triangle. So this window here is it's sort of the space of all triangles with some redundancy. The x coordinate is like one of the angles. It's like 2 pi times x, and the other angle, the y coordinate, is 2 pi times y, and then the third angle is determined because it's a Euclidean triangle. And you're looking at the famous Fagnano periodic billiard path. It works in any acute triangle. You can sort of see it's the triangle of minimum length that's inscribed. I was saying before that when you play billiards, somehow length is involved, and the billiard paths locally are the ones that minimize length. But then somehow when you get to here I'm going down to the right triangle case, and then the thing just disappears. This periodic billiard path no longer exists. What I'm drawing in this window is sort of the unfolding process. I'm taking the periodic billiard path, and every time I hit an edge, I'm just unfolding the triangle. So what you notice about this is that the first and last sides are parallel, and then there's sort of some upper vertices, and then there's some lower vertices, and the upper vertices are all above the lower vertices. And then if I take any straight line in this blue strip and fold it back up, I'll get the Fagnano path. So this is an example of a periodic billiard path which is stable. And what that means is that if I vary the angles of the triangle a little bit, the periodic billiard path remains. Now, if you go back to the square, like say on the square you just have the billiard path that goes like this, back and forth. But now imagine I take the square and I sort of make the sides go like, I tilt them outward a little bit. then the path goes and it kind of goes up a little bit, and it's not stable. So somehow, well, I got to show you some more pictures. I'll show you another stable periodic billiard path on the other side. I'll pick a point. I can push a button, and then here's this region here, and everything in here gives you this, the periodic billiard path you see over here. When you go to the edge, the thing kind of disappears. This blue.
And just to clarify, when you say the periodic path you mean over here, you mean the one with the same sort of coding, 1, 2, 3.
Yeah. So right, when you have a periodic billiard path, you get a sequence of 1s, 2s, and 3s. You just record the sides it hits, and if it's periodic, then you see a repeating sequence. And in this example, this example is also stable because when I vary the angles a little bit, the picture stays the same. The first and the last side remain parallel. So what I'm going to do is I want to talk a little bit about how does the stability work? Like what does it mean in terms of the sequence? So any questions so far? I'm just showing you a picture of a periodic billiard path.
In blue, it's a periodic stable orb.
Yeah.
But it's the smallest one, or no?
It probably is.
Okay.
Yeah, I'll say. I mean,
Smallest you can find.
yeah, it's the smallest you can find. Yeah, I'll say more about this in a minute.
I think you forgot to explain what the project business is about.
Oh, yeah. So what is this pink region? So this periodic billiard path, it has a certain, unfortunately it doesn't print out the words, but it has length 14, whatever it is. And you can ask, like, which triangles, so to speak, support this same sequence? Like, and then this pink thing is what supports it. So the pink thing is describing the region of things. So we call these things orbit tiles. So when I was first programming this thing, initially I thought, well, I'm going to solve this problem in a week. I'm going to just sort of go around and I'm going to like search for the periodic billiard paths, and I'm going to plot the tiles, and I'm going to cover the region, and then QED. But it didn't work out that way. So let me say, I'll say what the stability criterion is. When do you know if a sequence is periodic? And I think when you see this condition, you'll understand the difference between the rational and irrational case. Then I'll sort of say, well, how is the computer finding periodic billiard paths, and how is it plotting these regions that I've plotted? And then I'll just maybe show you the results of some experiments. Okay, so the stability, what's going on? Well, you have a periodic billiard path in a triangle, and you know after 14 steps, let's say, it comes back and it's going in the same direction. Well, every time you hit two sides in a row, like a 1 and a 2, you're first reflecting in the 1, and then you're reflecting in the 2. And so you're rotating by the direction is changing by twice the angle. So somehow this happens 7 times. You do like 1, 2, and that changes by twice the 1, 2 angle, and then maybe you do 3, 1, and that changes by twice the 3, 1. So if you have a symbolic sequence like 1, 2, 3, 1, 2, 3, etc., you're changing by like plus 2 alpha, plus 2 beta, maybe plus 2 gamma, and if the 3, 2 was reversed, then it would be minus 2 gamma. And when you're done, you want this sum to be 0. Now, if you have a rational say a rational triangle, then this is going to happen a lot because these numbers are rational. So there's going to be lots of weird combinations that are going to be just equal to 0 sort of by accident, by number theoretic accident. And this will produce a lot of periodic billiard paths. But if they're irrational and you're varying them a little bit and you want the sum to be equal to 0, somehow the kind of combinatorial coefficients you get when you just add all these numbers, they have to add up to 0. Because otherwise, like if there was some weird, mysterious combination, if you changed alpha a little bit, then the sides wouldn't be parallel. So there's a kind of, essentially what happens is the 1-2, you have to see a 1-2 couple as often as you see a 2-1 couple, and you have to see a 3-1 couple as often as you see a 1-3 couple, and likewise for the other one. So you can sort of take your sequence and inspect it, and you can look for this property. Now, okay, if it's odd, don't look at odd length periodic billiard paths. Just take 2 periods and double it. But anyway, there are several ways to say what this condition is, and here's one that Pat and I thought of, which is really says the same thing. What you do is you look at the hexagonal lattice in the plane. And you label all of the edges of one kind by 1 and all of the other edges by 2, and then the ones of the third kind by 3s. And then if you have a periodic billiard path or one of these symbolic sequences, it lets you take a ride on the lattice. Because you just, every time you see a 1, you take the 1, and every time you take a 2, you take the 2. And then the stability condition is exactly that this thing is a closed path. So that's another way to say it, and it translates into this thing I said before. So in this picture here, here's the ride on the. Oh, you can't see that.
So actually, I'm going to ask a stupid question here, which is
Sure.
the original Fagnano trajectory, the code's 1, 2, 3. If you do it twice, the code's 1, 2, 3, 1, 2, 3.
Yeah.
But then you're not seeing 1, 2, and 2, 1 the same number of times, right? And it's still stable.
1, 2, 3, 1, 2, 3. Maybe cyclically you are.
I see.
Yeah. Sorry, good point. Like here's the 1, 2. Okay, am I lying to you? Okay, that's a little embarrassing. Anyway, this condition really works. Yeah. Okay, so there's something. Maybe it's at like the 2. So here it appears in the second position. Here it appears in the 5th position, and you count the number of times it appears in an odd position, number of times it appears in the even condition. So it's something. Yeah. Okay. So, but anyway, the couplet thing. But this thing really works. This thing's solid. If you take the path and if it, yeah. No?
One way to think of it is if you're unfolding the polygon, it has an opposite orientation every other time, and so the angle adds the other way.
Yeah. I guess that's a good way. That's a good way to say it. But this another way to say it, maybe more canonically. Like you might wonder what happens for a quadrilateral. Like what, and you can take your triangle and double it. So just glue 2 copies along the boundary, and then remove the vertices, and then you can think of your even path as a closed path on the 3-punctured sphere, and then the condition is that thing should be 0 in homology. Now, why is that related in any way? Well, when you compute homology, you should always kind of, when you learn in algebraic topology class, you see it's a combinatorial thing and you can reduce it to a graph. So if you have a path, you can sort of push it on this kind of theta graph that's right in the middle. And now you have a path on a graph and you're interested in, 10 minutes. Okay. Okay, so that's the stability condition. I hope that made some sense. Yeah.
So is that lattice something of a dual lattice of the unfolded thing or something like that?
This, I would describe it as like the universal abelian cover of this theta graph. That's how I think of it.
So, okay. So what I should be thinking is that the order that sort of things are put on that lattice has to do with the order of
Yeah, that's right. Okay, so what is the computer program doing? So what it does is, you might be interested in words, you want to find all the periodic billiard paths of length at most 50 for a given triangle. So you fix the triangle in advance, and then you make a binary tree. So of depth 50. Maybe I'll turn on the light. So this tree represents all possible, symbolic sequences you could see in this business, say starting with a 1. Now, what is a depth first search? Basically, what the computer does is it sort of always goes to the left, and I mean, if uninterrupted, it would go all the way down to the bottom, and then it would back up, and it sort of makes the path around the tree, and then it just visits all the nodes, and it just skips all the ones it's already visited. But if you were going to do this, this is like 2 to the 50 steps. This is too big for the computer. So the computer is doing two things simultaneously. It is it's every time it draws a path, every time it considers some path in this tree, it draws the hexagonal path, and it asks, is it closed or not? If it's closed, well, if it's not closed, it says, that's not stable. This is not a good stopping point for me. I have to investigate further. The other thing it does is simultaneously, it draws the unfolding of the triangle with respect to this path. And if the unfolding is quite crooked, maybe I'll just give you a demo of this quickly. Here we've got this thing here, but if I go out here, the thing is starting to look pretty bad. So if it notices that the unfolding is crooked, so that not all the top vertices could be above all the bottom vertices, then it just eliminates the path. It says, well, there's no point in further searching because this thing is never going to straighten out. And I mean, well, I don't know. I mean, in the end, after a long time, I was in charge of the plotting and Pat was in charge of the searching. So Pat has some very kind of slick way of testing this. But a cheap test is something like you have what should be all the top vertices and all the bottom vertices, and you test them 3 at a time, like 2 tops and 1 bottom. And if the triangle of those points has the wrong orientation, you throw it out. So, I mean, you could sort of get a crude measure of failure. And then if it's failure, you cross it out, and then you prune off the branch and you continue your search. And then when you find a point where you have the stability condition, then you just check whether all the top are above all the bottom. And if they are, you win. You find a periodic billiard path. And if not, you just stop and eliminate the rest of the branch. Yeah.
Because if all the top are above all the bottom,
you have the corridor.
Right.
Yeah.
How do you know what angles to use?
You pick the triangle first. This is a search you do for a given triangle. Right. So that's what the searching does. And I think about 7 minutes. 6.
More? Yeah.
Well, I don't want. Okay. Well, so this thing goes around, and you can see it found 3 of them, and I'll pick another one. This one's longer. No, but I ought to be able to wrap this up. So here's. Yeah. Okay. So here's the here's the other one. It's smaller. And then here's the third. So let me show you a cool plot. Okay, so how do you plot things? Maybe that's the last thing, almost the last thing I'll say. Here's a way to draw a picture in the plane. So the plotting also works with like a depth first search. So you have the unit square. I'll just draw this dotted line just for you to remember. And you have some kind of mystery object you're hoping to plot. And what you do is you ask a question of any square, and the question is the square inside your object? And like if the square is some little piece like this, maybe you check the vertices, and if the vertices are good by kind of a wide margin and it doesn't look like things are varying a lot, you would actually include the square in the plot. And if you have some little square over here, you can see that the whole thing is just like if the vertices, it's just completely messed up, and you'd eliminate it. So you sort of do a subdivision algorithm, and at every square you either say yes, no, or I don't know. No means you eliminate it. Yes means it's literally inside or probably inside. And I don't know means you should subdivide it and then re-ask the question. So this thing goes through and it sort of does, I'm just showing you kind of the results of the subdivision algorithm for plotting. What's good about this is it finds everything. Like Pat and I think that these are connected. I think they're connected and simply connected. Pat doesn't even think they're connected. They look convex, but those sides are not actually straight lines. They're somehow complicated. You take a complicated trigonometric sum and you set it equal to 0. So anyway, we think that these tiles are all connected. I think they're simply connected and connected, but Pat doesn't even think they're connected. So it's a kind of a basic question. Like you pick a combinatorial type, and does the set of words. One thing, OK, so let me, maybe in the last couple of minutes.
Sorry.
Yeah.
The tiles you compute
Yeah.
are not polygons, but
They're not polygons, but we think.
tiles that are the stability regions for these things are making polygons?
What's that?
Is it that the thing you compute is not a polygon, but the ideal thing behind it?
The thing I compute is ultimately a polygon. But the actual, in fact, everything on the computer is a polygon. Whatever you want to do, it's always a polygon. But I mean, but somehow Pat thinks maybe the sides can be so curved that they would like bow into each other and make two regions. But another question is something like, what's the area of these in terms of the length of the billiard path? If the, kind of intuitively, if the path is long and you move a little bit, then the thing should, it's like a snake that wiggles. And so if you had a really sharp bound, say you could show that the area decayed like more than, faster than the length to the 4th power or something, then somehow the growth of the number of possible sequences that can work from triangles, the kind of complexity of that language is conjectured to be like polynomial. And say if you could show that the length of these pieces decayed exponentially, you could actually show the opposite, that sort of there's not enough of these regions to actually cover the thing. Let me just, all right, I just have to show, I'll show a picture. Let's just see. So what I proved, I went around, so let's see. So here's a kind of infinite family. Yeah. So here's the words. It turns out that around the 30, 60, 90 triangle, you can't find a finite list of tiles which cover a neighborhood. But nonetheless, there's an infinite family that covers the 30, 60, 90 triangle neighborhood. And then there's another family, well, right, so
So somehow the point, 30, 60, I mean, this goes back to something you said earlier, which is that on the torus, trajectories are kind of periodic trajectories are kind of unstable. And 30,
right.
60, 90 gives you a torus when you unfold it.
Yeah, that's right. All the paths on the 30, 60, 90 triangle are unstable. In fact, Pat Hooper, I think this was due to Pat, that every periodic billiard path on a right triangle is unstable. And so these tiles don't slop over from the acute to the obtuse region. But anyway, near the 30, 60, 90 triangle, you need this kind of you need this kind of infinite family. I'm clicking on it and you're seeing the different words. And then there's another infinite family sort of out here that kind of covers, I truncated these, but there's another family that kind of goes all the way out to the boundary of the space. This family goes up to 5 pi over 8. The angle, if all the angles are less than 5 pi over 8. And then there's the middle, which you have to fill in. So this is sort of demonstrating the fact that every triangle has a periodic billiard path if all the angles are less than 100 degrees. So you need infinitely many. But somehow you might wonder, like, why 100? And for this, I encourage you to watch George Carlin's video about why 10 commandments. And he said, why 10? And well, if they said 9 or 11, it just wouldn't seem that serious. It's a marketing decision. Anyway, so 100. I mean, the thing is, if you take a very thin triangle where the angle is more than 5 pi over 8, which is 102.5, it's not known even if you can cover a neighborhood of that point in the boundary. So, I mean, the boundary is completely exposed. And George Tokarski and his group, they got up to 102.3 using like a quadrillion paths or something. 112.3.
Yeah, that's the 5 pi.
So it's 5 pi over 8 minus a little bit. But anyway, I'd pay someone a lot of money if they could just get any near the boundary past 5 pi over 8. Okay, anyway, I think I'm out of time, so that's it.